Hey everyone, it's Dr. Calkins. Today we're doing week 15, chapter 12, solutions, second to last chapter of our semester. So here's some questions that were submitted. Starting with number 2, solutions are considered to be which general type of matter? We covered this back in week 1, chapter 1. Pure substances would be something like on the periodic table. So one of the 118 elements could also be a compound. Homogeneous mixture is the synonym for solutions that we want. Heterogeneous mixture would be something that looks different, and solutions look the same. And again, pure elements, pure substances, those are the same thing. So A and D really the same answer, just asked in a different way. And number 3, it says in a solution made by dissolving 50 grams calcium chloride, you have 1,000 grams water, which is considered the solute. Well, remember the solute is the little guy, and the little guy is the 50 grams of calcium chloride. So water, this would be the solvent. Together, they would make the solution. So we know those definitions well. Number 4, which of the following examples is a decrease in entropy? Entropy, another name for chaos or randomness. So if we're decreasing the randomness, we would be increasing the organization. So if you add cream to coffee, it's going to disperse, it's going to mix. So definitely not that one. That would increase the entropy because of the mixing process. If you assemble a jigsaw puzzle, it used to be a mess, now it's in a perfectly put together puzzle. That's what we want. Assembling a puzzle takes a lot of time because you're fighting entropy. You're fighting that piece that's probably lost underneath the table the entire time because of entropy. Ripping it apart, definitely going to make it chaotic or random. So definitely not that. And then melting is going to be from that organized cube into that disorganized puddle. And that would also be an increase in entropy, not a decrease. Then we get into some math problems. So number 7 says, what is the molarity of calcium chloride? So this is very similar to that first matching section you're going to see in the back. We'll see that a little bit later. So remember, molarity is capital M, and that stands for moles of the solute divided by liter of the solution. So in our case, we have 0.0025 moles. We divide by 3.68 milliliters. That's not liters. So we need to convert from milliliters, which is 1,000, to 1 liter. Milliliters cancel. Now we have our moles. Now we have our liters. Now we have molarity. So in our calculator, that would be 0.0025 divided by 3.68 multiplied by 1,000. And when that's typed in correctly, you get 0.679, and that rounds up to D. Number 8 says the solute in a saline solution. So solute again is the little guy. Saline solution is salt in water. So salt would be the small portion. Water would be the solvent. And if you add salt with a solvent, you're going to get the salt solution. Alright, and number 13, which one has the highest hydration energy? If you looked at the PowerPoint notes, you saw that higher charge would be higher energy. With a higher charge, you're going to attract more molecules strongly. It's also a good chance you're going to have more moles of ions in solution to have attractions. So magnesium is a +2, aluminum is a +3, silicon is a +4, assuming it's ionic and not covalent, sodium is a +1. So larger charge, larger energy, says silicon would be the winner here, assuming it's again ionic and it separates into ions. Number 16. Number 16, I believe, is a typo because it should say soap consists of a polar head, not long, and then it should be a long non-polar tail. So I'm pretty sure that's a textbook typo in this situation, but it's the same definition that we would have saw if we saw the notes and a little bit of that lecture. There's no long head, it's a long tail. It's hydrocarbon based and nonpolar. Number 19, back to some math problems. Here the keywords are dilute. Once we see that, we're going to know that it's M1V1 equals M2V2. See a question like this on the final exam, very similar to it. So notice there's a pair together and then there's a pair separate. So when we have this, we're going to just find any pair. So this was 0.4 capital M with 100 milliliters. So there's one pair of data. Look over here, we have 2M, but we need the volume. So we're just going to call that V, or like an algebra X. Divide by 2M on both sides. The M's go away, the 2's go away. Here, only the M's go away. So now we're ready for our calculator. Volume that we need of our strong solution would be 0.4 times 100 and then divided by 2. So I could have done that one in my head, but that's 20. 20 milliliters could be A or B. Remember, this is called dilution for a reason. If we add 20 mils of acid, we don't add more acid. If we had 20 mils of acid, we would add enough water to dilute it to a total volume of 100. So B is what we want there. Number 20, another math problem. This one is, notice, a milliliters to grams kind of problem. That's also a matching section on the back. So we're going to take that 25 milliliters and get rid of it by setting up a conversion where milliliters goes away on the bottom. Remember that capital M is a conversion, so this is capital M, it's per 1 liter, so per 1,000 milliliters, and this would be 0.1 moles. So we're using capital M as this conversion. Now we have moles, we want grams, so we need to get rid of moles next. So moles cancel. We know that grams on the periodic table can tell us 1 mole. So this would be Na plus Cl. We look on the periodic table, sodium is a 23 roughly, and chlorine is a 35.5 roughly. So we're looking at about a 58.5. Again, 35.5 and 23. So now we're ready for the calculator. So we take 25, multiply by 0.1, divide by 1,000, which was our conversion of a liter. Multiply it by the molar mass, 58.5, divide by 1 doesn't do anything, and we get 0.146. And that rounds up to the answer B. 0.15 grams. On this page of math, we have two that are very similar. We have milliliters to moles. So milliliters to moles is very similar to what we just did. We take 500 milliliters and we get rid of them. We know in 1,000 milliliters, that's capital M. So put capital M here, capital M in this case is 0.4. That changes for every problem. Milliliters cancel. Now we need moles. We need to go to moles of ions. So we can use the chemical formula here. If sodium nitrate is NaNO3, there is 1 sodium per 1 nitrate. So in 1 mole of the sodium nitrate solution, there is 1 mole of sodium ions. So here's this imaginary 1 becoming now a conversion. So there's 2 ways to have multimole ratios. It's from a balanced chemical equation, which we do not have, or it's from subscripts, which we have from our formula. So in this case, we have 500 times 0.4 divided by 1,000. So we get 0.2 times 1 over 1, we still stay 0.2. So it's 0.2 for sodium. If we were to switch this to nitrate with the NO3 and a negative charge there, notice it's still a 1. So it's the same problem again, so 0.2, 0.2, and that's A. And 24, very similar. So in this case, what we're going to have is 500 milliliters again. Same concentration, 0.4 moles per 1,000 milliliters, or 1 liter. We're just using milliliters, so it cancels. Don't need that extra metric conversion. Now we have 1 mole of calcium nitrite. Calcium nitrite, because calcium is a group 2 metal, has 2 nitrites. So it is still 1 mole of calcium ions, because this is a 1. So it's still a 0.2 for calcium, but then when we do nitrite, so when this changes to NO2 with a negative, now there's 2 of them, so this becomes a 2, and then 0.2 becomes 0.4, which in the end is also 8. So very similar problems using subscripts of our chemical formula. Pretty rare to use those, but that's one time we do use them. 25 says how many grams are in a percentage solution. So if you were to take, in this case, 200 grams and you times it by the percentage itself, you should get grams directly. So 200 grams times 0.10, and you get 20. So that's a quick one. So remember, percentage is piece of the whole, we're just going backwards in that situation. You could also take each one of these numbers, divide by 200 times 100, and you get that 10% back, if you wanted to work it in reverse. Phenolphthalein, if you watch the lab for experiment 23, you'll see, and these questions are similar to what you see on the back of this homework, you're going to see that it turns pink when you add base. It starts out clear. Blue and orange are never going to be visible with this particular indicator. Number 29. Multi-step problem here. We have molecular mass, so we need a balanced chemical equation because we have acids and bases. So if we have this monoprotic HA acid and we add sodium hydroxide, it does a double replacement. You get Na with a capital A, and then you get HOH. So what we end up with is a 1 to 1 to 1 to 1 balanced chemical equation. So I have to do that first. There's a couple more problems like this later. We know that molecular mass is grams over moles. We have grams, which is 0.2119 grams. We just need moles. So if we take these and we can convert, find those moles directly. So if we take our 34.7 milliliters, we have to get rid of milliliters. We know that in 1,000 milliliters, and this was specifically of the sodium hydroxide, so we need this conversion, 0.0500 moles. So again, this is capital M as a conversion. We've seen that a couple times now. This is of sodium hydroxide, so we need to cancel moles of sodium hydroxide and go to moles of HA. We found in the equation that was a 1-to-1 ratio, so this is just 1 to 1. So what we really need is 34.7 times 0.0500 divided by 1,000 times 1 over 1. So we get this very small number. We throw this number underneath, so 0.001735 goes here. We take 0.2119 and then we divide by 0.001735 and we get a mass of 122. Number 31 and 32 are almost identical to what we just did. They just have different acids, different bases. So we're going to need balanced chemical equations for these. These are titration problems. This is just like the one we just did because HCl is monoprotic acid, so it's going to make sodium chloride and water, HOH. So that's a 1 to 1 to 1 to 1 balanced chemical equation. Here we have the acid. So it's 10 mils of the acid A, base B. So I'm just going to use those labels to make it a little bit easier and cleaner. Milliliters of A, there's 1,000 in a liter. The concentration is 0.5 moles of A. We need to cancel moles of A. There's 1 mole of A to 1 mole of the B base. And then in 1,000 milliliters of the base, how many moles? That was provided over here at 0.5. So notice here, 0.5 and 0.5 cancel, 1,000 and 1,000 cancel, 1 over 1 is 1, times 10 is 10. So that one you could do in your head, as long as you know how to set it up. And number 32, very similar kind of problem, just different setup. So in this balanced chemical equation, we have a diprotic acid, H2SO4. We have ammonium hydroxide, which only has one hydroxide because ammonium is a +1. You'll get ammonium sulfate and water. You'll get 2 waters because it takes 2 acids and 2 bases to neutralize and make water. So this is a 1 to 2 to 1 to 2 ratio. They give you 10 mils, so it's the exact same setup. So we'll just reuse this one. Again, here's the acid, here's the base. They have 10 mils, just like the previous problem. This is of the acid, 0.5, 0.5, 0.5, 0.5. And now the only major difference here then is sulfuric acid is the acid that cancels on the bottom. There's one of those, so this one is still good, but now our base has a 2. So since we need twice as much base, we're going to need twice as much of the 10 mils, which is going to make this 20 mils. So the only major difference in the third one that wasn't asked but has the same setup is now the acid to the base is going to be reversed. So in that one you're going to need twice the acid, and you're going to have to cut that one in half. So since magnesium hydroxide has 2 hydroxides, you're going to need half as much of the 10 mils, so that's only going to be 5 mils. But same problem, just different numbers. Number 37 is a conceptual question. Remember that like dissolves like. So carbons and hydrogens, if we look at electronegativity, carbon is a 2.5, hydrogen is a 2.1. So we would say nonpolar. That 0.4 difference isn't the 0.5 large that we need. Carbon tetrachloride, carbon is 2.5, chlorine is 3.0, so that is 0.5, but it's 0.5 in a 4-way tie, which is also nonpolar, and like dissolves like, so nonpolar will dissolve nonpolar, so that is true. So that's a trick question because carbon tetrachloride was one of those we said watch out for because of its shape. It actually is nonpolar even though its bonds are polar. CO2 and SO3 were the other 2 examples we said watch out for back on exam 3. Vinegar. Vinegar is a liquid solution, which is true, where acetic acid is the solvent. When we did our experiment 23, which is over this lab, it's over this chapter, vinegar is 5% acetic acid in water. So water is the solvent. Acetic acid would be the solute, the little guy. It's only 5%. 95% water is the big guy, that's the solvent. So in this case, it's backwards. 47 is more of a trivia question. The bends is a condition where divers, when they go too deep, too fast, or rise too quickly, the oxygen or the nitrogen in their blood can depressurize, make them sick, make them have nausea, that kind of thing. That is true. Very similar to catching fish very deep and pulling them up too quick. The little air bladders can actually kill the fish. So again, a trivia question more than anything about solubility of gases in liquids. You need high pressure, which is common at deep depths, and cold temperatures, which is also typically in deep water. All right, last page. We have lots of math problems here. Did a couple, almost an example of each one of these on previous pages, so these will go fairly quickly. These are capital M problems. That's moles over liter. So here we have moles, which is 2. Moles over liters, which is not given, so we're going to have to convert 4,000 milliliters. There's 1,000 milliliters and 1 liter. Milliliters cancel. So you take 2, you divide it by 4,000, and then you multiply by 1,000, and you get 0.5, which is down here. Number 57, a little bit easier. because here when you take capital M, which is moles, 0.5 moles, you already have liters. So just divide 0.5 divided by 4.5. You already have the units you want. This one you get 0.11. So that one matches up here. You'll be able to do the other two based on those. 59 through 61 have the same setup, just different numbers. So in this case we have milliliters to grams, and I believe we did this on a separate question for multiple choice earlier. 25 mils, get rid of mils. And the way to get rid of milliliters is 1,000 per capital M. So capital M goes here. Capital M in this problem is 0.1, that always changes. It's always different per problem. This only gives you moles. We need to go one step further and get rid of moles, go to grams on the periodic table. So this would be NaCl in this case. We did that in an earlier problem. This would be 58.5, that's 23 for sodium and 35.5 for chlorine. Multiply those across. So 25 times 0.1 divided by 1,000 times 58.5. 0.146. So straight across. So very similar setup in the next one, it's got liters. So let's try it, very similar setup, and then once we know it, we'll know the last one by default. So we have 1.50 liters, so now we don't need 1,000 milliliters, we can just say 1 liter, because now liters cancel instead of milliliters. Capital M is top again, so 0.0694 goes here. Moles need to cancel. And 1 mole we need up here, grams from the periodic table for cesium hydroxide, so CS and then OH. So cesium, way over here at 132, so 132.91 roughly, plus oxygen at 16, plus hydrogen at about 1.01. 149.9 goes here. So that's cesium plus plus oxygen plus hydrogen. So we take 1.5 multiply by 0.0694 multiply by 149.9 divided by 1 twice doesn't do anything, and then we get 15.6. So now we know who the other one has to be, which is straight across, same setup, 125 mils. So that one's going to be more like this one, where you put 125 out front, you change this to a 0.0250, and you change this one to 12 carbons plus 22 hydrogens plus 11 oxygens in mass, and then you'll get the remaining answer. 62 through 64 is the reverse. So here we're going from grams to liters. So take grams, 47 grams, and get rid of them, go to moles, and then go to moles back to liters. We know that in 1 liter, capital M, so that's 0.15. So there's capital M just now in a reverse position from the previous problem. We know that 1 mole is from the periodic table. The periodic table here is nickel sulfate, that's NiSO4, added up on the periodic table. So nickel, 58.69, sulfur, 32.1, and 4 oxygens plus 4 times 16, 154.79 goes here. Grams cancel, moles cancel. So now we have in our calculator 47 divided by the mass to get rid of grams, 154.79, divided by molarity, 0.15, and we get 2.02. So very similar on the next two. We have 20 grams. Get rid of grams, go to moles. 1 mole in the periodic table for HNO3 goes here. get rid of moles. Moles come from capital M. Capital M here is 0.32 moles per 1 liter. So again, this is capital M, just upside down. HNO3, hydrogen at 1.01, plus nitrogen at 14, plus 3 oxygens at 16. So 63, and 01. So we take 20, we divide it by 63.01, we divide it by 0.32, and we get 0.99, which is back up to 8. So now we know what the other one has to be as a result, but same setup. Put the 437 out front, put the 1.1 underneath, find the mass of lead nitrate. Lead nitrate is PbNO3 twice. So same kind of setup, grams, again 437 out front, the mass of lead plus 2 nitrogens plus 6 oxygens underneath, and then the concentration, which is now 1.10 at the bottom, to get that final answer. Lastly, these are just definitions that come from experiment 23, drop the base. When you do this, you use a burette, so that's the device, the piece of glassware needed in order to drip the base into the acid or vice versa to neutralize it. The equivalence point is the point at which we have equal amounts, so that's when they're equal. That's when that color change starts to happen. And then the titration is the process of adding it from the burette to get that color change that you hopefully saw in the video. And that'll do it for the solution chapter.